Polymers are examples of very large molecules in chemistry that involve repeating monomer units. As an example, a diamine can react with a diacid chloride to make a polyamide. In this example, we're actually synthesizing nylon, which is one of the most important synthetic fibers. This type of reaction involves an acyl substitution. It is also a type of condensation reaction. We have covered several of them already. Condensation reactions are reactions where two molecules will join together to form a larger product, an addition product, leading to also usually a byproduct, a small molecule that is a byproduct. Here's another example of a condensation polymer, which involves a diol reacting with a diacid. And so one of the alcohols attacks the carboxylic acid through an acyl substitution to make a polyester. And if that reaction repeats multiple times, we can make a polyester or a polymer involving ester bonds. There are two main classes of synthetic polymers. The one we're looking at here is a type of step growth polymer where each bond is individually made, leading to a product and then reacts further. It can be the same type of reaction, but each step produces a new bond. Last semester, perhaps you encounter a different type of polymer which was formed from the reaction of alkenes, adding a radical initiator such as benzoyl peroxide and adding either heat or ultraviolet light led to the beginning of the reaction. But once the reaction got going, multiple bonds would form consecutively in the reaction. And so that would be an example of what we call chain growth polymers, where multiple bonds are made in the same reaction. Let's take a look at other examples of condensation polymers. Nylon 66 is an important synthetic fiber. It can be made from a dicarboxylic acid, such as adipic acid, and diamine, such as hexamethylene diamine. If we heat the two, we can form an amide bond multiple times. So one of the nitrogens can replace the OH group on a carboxylic acid. And if we repeat that multiple times, we'll end up making a polymer, which we call nylon 66. Each reaction will make an amide bond, but that reaction continues, and over we continue to make amide bonds. Notice how we draw the product from one of these polymerization reactions. So we typically abbreviate the monomer unit that we're using. So in this example, we have the diamine, which we used, which was hexamethylene diamine. You can see that on the right side. And then on the left side, we have most of the adipic acid minus the OH group, since now the carbonyl is joined to the nitrogen. And then on this side, we have a carbonyl that's bonded to another nitrogen, which of course is not shown. It's shown on the right-hand side here as these units are repeating. We put this all in a parenthesis to put a subscript N to indicate that this monomer is repeating multiple times. Another example of a condensation polymer is dacron, which is another synthetic fiber that would be made from dimethyl terephthalate, which is shown here as a diester. It reacts with ethylene glycol, which is antifreeze, of course. This is a diol, and so you can replace the methoxy group to make an ester bond, and if you repeat them multiple times, you'll get the polymer. Again, the polymer product is abbreviated here in parentheses with a subscript N. Condensation polymerization reactions can also be used to make biodegradable polymers, and there are 3 examples shown on this slide. Biodegradable polymers typically will contain an ester bond, which is, of course, is susceptible to hydrolysis over time. There are 3 examples shown here. The first one is made by taking a compound that has a carboxylic acid and an alcohol, and of course, repeating these units multiple times. One alcohol from one unit can react with a carboxylic acid of another. Same thing happens in the other 2 examples. So we have lactic acid and we have this 3-hydroxybutyric acid. Each of them contain an alcohol and a carboxylic acid. Is an example of a thermoplastic. It's essentially a impact-resistant glass, which is made by taking a compound called diphenyl carbonate, which has a carbonate functional group. It's essentially an ester, except that it has 2 alkoxy groups rather than just one. This functional group reacts with alcohol similar to esters, and so if you heat them up, you can make ester bonds and therefore make Lexan. There are many important biological polymers, including cellulose, proteins, and nucleic acids. Cellulose is a polymer of glucose, so 2 glucose units can join together by the reaction of this alcohol and this alcohol on 2 different units. So that leads to the formation essentially of an acetal. So you can see here on this carbon, we have an alkoxy group in this direction, and then we have an alkoxy group in this direction. So that makes this carbon an acetal. So glucose itself is a hemiacetal, and if we take the alcohol unit of 1 glucose units and react here, it'll lead to the formation of this bond here and essentially formation of an acetal. Proteins are polymers of amino acids. So amino acids contain both a carboxylic acid and an amino group. And so one amino acid can react with its carboxylic acid with the amino group on a different amino acid. And that leads to the formation of amide bonds and therefore the formation of a protein. Nucleic acids like RNA and DNA are polymers of nucleic acid bases. So here's the structure of a nucleic acid base that would react involving the alcohol of one unit with the phosphate group of another to make these phosphate bonds and connect different nucleic acid bases. Let's take a look at this problem involving condensation polymerization reactions. So in this reaction, we have a dihalide and a diol, and we're going to add base to form a polymer from it. Now note this is not a acyl substitution reaction, is actually a simple SN2 reaction which we looked at earlier this semester. When we have a dihalide and a diol and we include base, one of these alcohols will react with the carbon with the leaving group, doing an SN2 reaction. And if we repeat that multiple times, we'll eventually make a polymer. So that leads to a polymer that has this structure. And you have here on the left side, the 3 carbons from the alkyl halide. And then that's bonded to an oxygen, which would be this one, let's say, with 3 more carbons, which would be the 3 carbons in the diol, plus another oxygen, and then a bond to the next unit. All of this is put in parentheses with a subscript N to indicate that we have a polymer of variable units.